Hello everyone, welcome to today's video. In today's video, we will solve the pressure vessel shell in Ansys software and compare the outcome with the theory of thin and thick cylinders. This video discusses the following subjects. We will first go over the definition of pressure vessels, the theory of thin and thick cylinders, and the lame analysis. Two problem scenarios will be simulated in Ansys Workbench, and the outcomes will be compared using both theories. Pressure vessels are containers for the containment of pressure, either internal or external. This pressure may be obtained from an external source or by the application of heat from a direct or indirect source, or any combination thereof. In the industrial sector, cylindrical or spherical pressure vessels are frequently employed as storage tanks, reactors, and boilers. The thickness of the cylinder relative to its inner radius is one of the main criteria used to categorize pressure vessels. There are two types of pressure vessels: thin wall pressure vessels with an inner radius to thickness ratio greater than 10, and thick wall pressure vessels with an inner radius to thickness ratio less than 10. The stresses acting in the wall of these vessels can be analyzed in a simple manner using biaxial loading, provided it has a thin wall. That is, the inner radius to wall thickness ratio is 10 or more. Specifically, when the inner radius to wall thickness ratio equals to 10, the results of a thin wall analysis will predict a stress that is approximately 4% less than the actual maximum stress in the vessel. For larger ratios, this error will be even smaller. On the other hand, the stresses in thick wall cylinder varies over thickness, and the analysis is based on the triaxial loading, but for the design purpose, only maximum stresses considered. For the analysis, we'll assume that the pressure in the vessel is the gauge pressure. That is the pressure above atmospheric pressure. Since atmospheric pressure is assumed to exist both inside and outside the vessel's wall, now we will look at the thin cylinder theory. This cylindrical vessel in figure 1a has a wall thickness T, inner radius R, and is subjected to an internal pressure P. And to find the circumferential or hoop stress, we can section the vessel by planes A, B, and C. Here, only the loadings in the X direction are shown. They are caused by the uniform hoop stress, sigma 1, acting on the vessel's wall and the pressure acting on the vertical face. For equilibrium in the X direction, we require internal stress shall be equal to the pressure applied. Thus, we get circumferential stress equal to pressure times radius divided by thickness. Similarly, the longitudinal stress can be determined by considering the left portion of section B, figure 1a, as shown on its free body diagram. Figure 1c, sigma 2 acts uniformly throughout the wall, and pressure acts on the section of the contained fluid. Since the mean radius is approximately equal to the vessel's inner radius, equilibrium in the y direction requires internal stress shall be equal to pressure applied on the cross-sectional area of the cylinder. And then thus we get the longitudinal stress equal to pressure times inner radius divided by 2 times the thickness. By comparison, note that the hoop or circumferential stress is twice as large as the longitudinal or axial stress. Therefore, the hoop stress is the governing stress to determine the thickness of the cylinder. Now we will look at the thick cylinder theory. The analysis for thick vessel is first done by French mathematician Gabriel Lane, including the development of equations that describe the stress distribution in thick-walled pressure vessels. The result of the analysis is stress distribution in circumferential and radial direction. Now we will define our problem definition. We will consider two cases, and we'll simulate both cases in the Ansys Workbench. Case 1 involves a thin cylinder with an inner radius to thickness equals to 20. For a thick cylinder, case 2 with an inner radius to thickness equals to 4. In both situations, the length will be 1.5 meters long, and the pressure will be 50 megapascals. The geometry details and analytical stress calculations are shown on the respective tables. axis symmetric modeling will be employed. Simple 2D components are used to model solids with an axis of symmetry, or solids of revolution with axis symmetric loading and support. All stresses are independent of rotational angles. For instance, axis symmetric modeling can be used to flywheels, bearings, and pressure vessels with thin or thick walls. In this problem, we will not model the closure, instead use equivalent effects using symmetry to the edge, and thrust loading at other edge equals pressure times the cross-sectional area of cylinder. Now we will simulate case 1 first, drag and drop static structural into the project. Since stress is the only thing we are interested in, we will be using default material for this problem. Open Design Modeler, select unit as millimeters, draw a rectangle as indicated with a radius of 650 millimeters and a thickness of 32.5 millimeters. Uh, 1.5 meters is the length to be given. The default axis of symmetry in Ansys is the y-axis. Generate the surface using surface from sketches. Change analysis type from 3D to 2D. Now open Ansys Mechanical. Select 2D behavior as an axis symmetric under the geometry tab. Generate mesh with global size as 2 millimeters. This can take some time because we are creating fine mesh. At the upper face, insert a frictionless support. Likewise, apply pressure on inner edge with value of 50 megapascal and insert force on the bottom, face equivalent to the predicted thrust force. Now click on Solve. After solving to create a result of circumferential stress using normal stress in z direction, as we see, the maximum circumferential stress occurs at inner surface and decreases across the thickness. Likewise, insert radial stress in x direction. And longitudinal stress in y direction. Similarly, minimum radial stress occurs at inner surface and goes to 0 at outer surface. To plot the stress distribution, first create the path across the thickness as shown. Duplicate the circumferential and radial stress and change scoping method to path and choose the created path. To see hole geometry as cylinder, first turn on beta options in the Ansys setting. Insert symmetry and choose 2D axis symmetric use angle as 10 degrees with number to repeat as 37. Now click on any result to see hole geometry. Now to simulate case 2, duplicate the static structural and only edit the thickness rest of the setup is same as previous. Generate mesh and click on solve. Post process the results. As per the stress distribution, the maximum circumferential stress occurs at inner radius and minimum occurs at outer radius. The minimum radial stress occurs at inner radius and goes 0 at the outer radius. The longitudinal stress is uniform throughout the thickness and along the length. Since we have made a copy of the case, edit the path according to the current geometry as shown. One important thing in Cylinder is that the stress distribution is not linear. This indicates we should use second order element for accurate solution. To see hole geometry, use symmetry with 2D axis symmetric as shown for thin cylinder case. This slide shows the result of case 1 compared with both thin and thick cylinders theory with the percentage error. Here is the stress distribution of hoop and radial stress. As we can see, thick cylinders theory excellently match the Ansys results. This slide shows the result of case 2 compared with both thin and thick cylinders theory with the percentage error. Here is the stress distribution of hoop and radial stress. Here also, thick cylinders theory excellently matches the Ansys results. Based on the outcomes and simulations that were run, the following observations have been made. The thin cylinder theory calculates constant stress at minimum radius and predicts the average stress instead of the maximum stress. The longitudinal stress calculated from thin cylinder theory underpredict the stress when compared to Ansys because of the assumption of mean radius equal to the inner radius. Thick cylinder theory accurately predicts the maximum stress and results of Ansys aligns with the thick cylinder theory. One should always use thick cylinder theory for designing, finding the required thickness of the shell until the longitudinal stress governs the thickness of the shell. The problem we have simulated only considers the shell and head closures are not modeled for the simplification, but equivalent effect is considered in the analysis using the thrust force. For a more accurate solution, one should model complete geometry, which can reveal high stresses areas and stress concentration, which is important for fatigue analysis. The following are lists of references for further reading. Did you think about this? What is the actual formula used in the industry to find the thickness of the shell? Are you aware of the design code used for designing pressure vessels? Thank you for watching this video.